So as a reminder, in the Momentum Lab, we set up a ramp, much like we did in the Velocity Lab, and released a cart from 40, 60, and 80 centimeters. And then we measured both the velocity, we calculated the momentum, and then we also measured the distance a binder moved following impact with the car. So with measuring the distance the binder moved, we're actually measuring the transfer of momentum based on that impact. So, like always, you cannot take these two sentence starters word for word, but you can use them for inspiration. So remember, in our discussion paragraph, the first thing that we need to do is have an intro. And in that intro, it should be one sentence about kind of the purpose of the lab, and then a second sentence on the setup of the lab. So here I kind of give you an example of the setup question. We would still need the purpose sentence. So that should be one sentence, and this should be one sentence. A purpose sentence would be something along the lines of, in the Momentum Lab, students investigated the effect of release height on momentum and on the distance a binder moved following impact. Something along those lines, right? And then we have a setup sentence where we're talking about how the ramp was set up and where we released the cart from, and the two things that we measured and the one thing we calculated. We measured velocity, measured the distance the binder moved, and we calculated momentum. The second part of the paragraph will be results. We want a general statement, and then we want specific details. This should be about a sentence. This should be about a sentence. The general statement is right here, an example of that. You cannot use that word for word. These two sentences, remember, are inspiration. But the general sentence is basically that with a higher release point, velocity, momentum, and distance the binder moved are all increased. For the specific sentence, this one, you can copy this word for word because I'm trying to show you a very concise way of writing. So we would say that from the 40, 60, and 80 centimeter release points, respectively, the velocity was blank, blank, and blank, momentum was, etc., and distance the binder moved was, etc. So again, remember this respectively means that this first, second, and third data sets will correspond to 1, 2, and 3, 1, 2, and 3, and 1, 2, and 3. So make sure that they stay in those same orders, always 40, 60, and 80. Then we get to the actual discussion portion. And the discussion portion needs to cover why, then it needs to talk about error, and then it needs to talk about future experimentation. So to dive into this a little bit, when we're talking about why these results here occurred, we need to explain first the series of events that occurred. So the series of events is right here, right? So you increase the release point or the height from which the car is released. That's going to change the amount of distance that the car travels. As that car travels for a greater distance, that means that it's going to be traveling for a longer amount of time and therefore has more time to accelerate. As it accelerates for longer, it will therefore reach a higher velocity. Since momentum is calculated by taking the mass of the car times the velocity, and we know that the velocity has increased from 40, 60, and 80 centimeters, therefore the momentum will also increase from 40, 60, and 80 centimeter release points. Now we've just done this part and this part. Then that car that travels down the ramp is going to collide or hit the notebook at the bottom of the ramp. That is then going to transfer that force, right? So at that point, you've covered this first one and the second one, right? Talking about transferring the force or just mentioning transfer of the force is how you get a 3, right? What we need to do if we really want to get a 4 when we're talking about the force of impact and transferring of the force is talking about the deceleration of the car. So that takes a little bit more attention and focus here. So when we're talking about force of impact, that car traveling, if this is the ramp, right, and this is the cart, it's traveling down here and it's going to hit the binder. Bang, force of impact, right? So as long as you say that it transfers the force and it causes the binder to move, that's basically getting you a 3, right? You've covered the series, you've talked about the momentum equation, right? As the velocity increases, the mass stays the same, momentum increases. And then you say it collides with the book, transfers force, blah, blah, blah. But the difficult thing here is explaining force of impact and why the book moves further. A very simplistic answer is the book moves further because there was more momentum. But really, we know that the book moves further because of force. That car transfers force, it transfers momentum in this collision. So why is that force greater? We know that the cart is accelerating at the exact same rate, right? The acceleration doesn't change because the gravity doesn't change. But we know that it has reached a higher velocity when it's released from 80 than when it's released from 40. So let's make up some numbers here. When it's released from 80 centimeters, let's say that it reaches 10 meters per second of a velocity. When it goes from 40 centimeters, let's say that it only reaches 1 meter per second. Now remember, these are numbers that I just made up. The difference is that we're talking about this cart decelerating in the same amount of time, instantaneously. Let's call 1 instant 1 second. Now, as we talked about when we were talking about instantaneous speeds back in September, we know that an instantaneous velocity and something happening instantaneously is much smaller than a second, right? Something happening instantaneously is a thousandth of a second, right? A millisecond, or even smaller than that. But for our mathematical sake, we'll talk about 1 second here. So if this cart decelerates from 10 meters per second in 1 second, let's calculate the acceleration. Its second velocity is 0 minus 10 meters per second over 1. We're going to find that it has a rate of acceleration or deceleration of 10 meters per second squared. Here, it's going to be 0 minus 1 meter per second over 1 second, which gives us negative 1 meters per second squared. Now you math whizzes see where I'm going with this. If force is mass times acceleration, has the mass changed ever? No, it's still the same car. Let's pretend that the car is 1 kilogram, again, for mathematical easiness. So the force here is going to be 1 kilogram times a negative 10 meters per second squared, which gives us negative 10 newtons. So a force of impact of 10 newtons. Here, the force is going to be 1 kilogram times negative 1 meters per second squared, or negative 1 newtons. So what we have found out is that with our made-up mathematical numbers, releasing the cart from 80 centimeters instead of releasing it from 40 centimeters is going to produce 10 times the force of impact. Now again, these numbers are all made up. You shouldn't actually talk about 10 times because I made up these numbers. But the point is that the faster the car is going, meaning the higher the velocity of the car at the point of impact, it will result in a greater force of impact because it will decelerate in exactly the same amount of time. Let me restate that. So as the car is going from a higher velocity, meaning faster, it's going to decelerate in the same amount of time as a slower velocity, because that happens instantaneously. Instantaneously. Spelling. So because you've got a higher velocity, it decelerates in the same amount of time, meaning that your rate of deceleration goes up. And if your rate of deceleration, meaning your negative acceleration, is bigger, then your force will be bigger. So if we go back up here and we swivel back over here, when we're talking about force of impact at the end of this whole series of events, right? We've got a higher release point, which means more distance, which means more time to accelerate due to gravity, which means that the cart will reach a higher velocity, which, because of the equation, we know that since it's the same mass but a higher velocity, it will therefore have more momentum. It's therefore going to transfer that momentum to the book, which therefore transfers the force. Now, the reason the book actually goes further is because that force of impact is greater. And why is that force of impact greater if gravity never changed? Well, the force of impact is greater because as you release the cart from a higher release point, that faster car will now decelerate at the same instantaneous speed, which means that its rate of deceleration is faster. It's a bigger deceleration, a bigger negative acceleration. And with a bigger negative acceleration, what you're left with is a bigger force, because your force is your mass times your acceleration. So if your acceleration just got bigger, your force will get bigger. And remember that this force of impact is not because gravity increased. It is not because the car that's released from 80 centimeter accelerates faster. That is not the case. The cart did not accelerate faster. They all accelerated at the exact same rate because gravity acts on them at the exact same amount because they're all released on the same ramp. What happens differently is that it decelerates. Decelerates at a higher rate because the initial velocity is higher. So this is the part that's true. Gravity did not increase, gravity did not get any stronger, which means that the 80 centimeter car, the car released from 80 centimeters, doesn't actually accelerate or speed up faster. What happened is because that 80 centimeter car is going faster at the point of impact and it decelerates instantaneously, therefore that rate of negative acceleration will be higher, which means that the force of impact will be higher. This is the hardest part of the lab. If this is, give it a shot, but if you don't get this, this is one part of the entire lab. Don't get hung up on this point. This is the differentiator. Then we move on to talk about errors. Once again, we are not focusing on human error. What we are focusing on are things that are different between your lab and somebody else's lab group. So if my lab group is using slightly different materials, my car is a little different, my ramp is a little different, my notebook is a little bit different, those things are what provide the errors. What we're looking for is, is there a reason, that Group A has different numbers than Group B, right? And not because Group A did it right and Group B did it wrong, but because of what Group A has for materials compared to Group B. Finally, for future, we should once again focus on keeping the dependent variable the same. The dependent variable was measuring velocity, which then gave us momentum, and measuring how far the book moves. We should keep those two things. We need to keep the track. We need to keep the cart. All that we're trying to change is the independent variable. What do you want to test now with the same track, with the same cart, and still measuring velocity and the book moved? What else can we change to see if the velocity and momentum go up and the book moved also goes up? Right? What other thing can we manipulate? So once again, when you turn this in, here's a little picture, right? It should have your name. It should have Momentum Lab. You should have your data table. And this will include all trials. It will include velocity. It will include momentum. It will include how far the book moved. Then we need the graphs. Why am I drawing 3 graphs? Because you have 3, 1, 2, 3 graphs to do. Now those 3 graphs should just be the averages. You do not want all trials. All trials only show up in the data. Then you have your paragraph. And the paragraph, as we just discussed, goes through these different points. Starts with the intro and gives kind of the purpose of the lab and then the setup of the lab. 2 sentences. Then talks about the results, a general statement and a specific statement. Then in your discussion portion of it, we talk about why. Why did these results happen? Which is because of the series, which includes the momentum equation, and if you're really good, does a nice explanation of the force of impact. Then you talk about errors, not focusing on human errors. Then you talk about which future experimentation do you want to do.